Hi everyone, and thank you for watching this talk. I'm Kenneth Hoover, and I'm going to be presenting a lifting theorem for constant depth circuits and its application to the MCSP problem. This has been a joint work with my co-authors Marco Carmosino, Russell Impagliazzo, Valentine Kabanets, and Antonina Kolokolova. So I'm going to start off with a little bit of a riddle. What do multi-billion-dollar chip design companies, Leonid Levin and Dick Karp, have in common? They're all interested in the problem of finding small circuits for a given function. So when I say they're interested in finding the small circuit for a function, what I mean is the following problem, the minimum circuit size problem. Given the truth table of some function, what is the size of the smallest circuit that computes this function? Given that this is such a fundamental problem, we would like to be able to answer some fundamental questions about it, such as, what is the complexity? Is it NP complete? Despite being studied for many years, we don't actually know the answers to either of these questions. Our contributions to this area are the following. First, we give a lifting theorem from low constant depth circuits to high constant depth circuits for both worst and average case hardness. And we also get corresponding reductions between MCSP problems for these depth classes. What we'll be focusing on in the talk today is specifically the worst case complexity lifting theorem and reduction. We also get a new blockwise switching lemma that is a key part of making our proof go through. Finally, we give win-win arguments that say if we had a more efficient lifting theorem, then we would get circuit lower bounds or a more efficient MCSP algorithm out of it. This gives a natural barrier to improving these reductions. So why should we study MCSP? Well, first off, we could think of it as this abstract version of VLSI, the very fundamental applied problem of actually designing circuits and laying them out into space constraints or whatnot. On the complexity side, we get interesting consequences depending on the complexity of MCSP. If MCSP is in P, then we have collapses between randomized complexity classes. We have that crypto fails to exist, since we can think of MCSP as a super strong natural property in the Razvarov-Rudich sense. And we also get that general circuits are pack-learnable with membership queries over the uniform distribution. If MCSP is NP hard, though, then we get a separation between exp and ZPP that's not currently known. We also get a separation between exp and the intersection of NP and P poly. And we also get circuit lower bounds out of this, if this reduction has certain nice properties. So, with all that being said, why are we still studying this problem? Why haven't we, resolved it? What makes this difficult? And for simple circuit models, such as DNFs or DNFs with parities, we actually do have NP hardness results for the corresponding MCSP problems. Naturally, you would think, oh, if MCSP is hard for simple circuit models, then, well, for more complex models, such as arbitrary circuits, the MCSP problem should be harder, right? That's not so. For general circuits, we actually have negative results in terms of proving it's NP hard. That is, we have certain problems that are irreducible to MCSP under certain classes of reductions. And in fact, these classes of reductions are actually powerful enough to express most of the natural NP completeness proofs that we have today. So if we were going to prove that MCSP is NP hard, we'd actually need very different looking proofs than what already exist for other sorts of completeness results. Very recently, Alongo showed that constant depth AC0 MCSP for formulas is NP hard under randomized quasi-polynomial time reductions. Comparing our results and Alongo's, we both get lifting theorems between different circuit classes. For Alongo, his lifting theorem goes from depth D formulas to depth D plus 1 formulas, and the resulting output formulas can be constructed in randomized quasi-polynomial time. Whereas for us, we go from bounded bottom fan-in depth D circuits to bounded bottom fan-in depth D+1 circuits, and our output function can be constructed in deterministic quasi-polynomial time. In terms of NP hardness results, Ilongo can use the existing results for DNF MCSP hardness and lift that to any constant depth formula hardness. For our case, there is no known hardness results for bounded bottom fan in AC0 depth 3 MCSP. So talking about lifting theorems, a lifting theorem for two models of computation A and B just relates the A complexity of any function f to the B complexity of some related function f prime. Usually, we say that A is some sort of weak model where it's easy to prove lower bounds, and B is a stronger model where it's harder to prove lower bounds. And the idea behind a lifting theorem is we can take lower bounds in A that are easy to find, and mechanically produce lower bounds in B that are harder to find. We have various lifting theorems from decision tree models to communication models. The one-sided cover deterministic, non-deterministic, and probabilistic versions of each of those models. And ours is just going to show that when A is low-depth bounded bottom fan-in AC0 circuits, we can lift the complexity of those functions to depth D plus 1, or more generally depth D plus any constant AC0 bounded bottom fan-in circuits. So the first complexity measure we'll be talking about today is the constant depth alternating circuit size of a function, denoted as AC0 sub, in this case, D plus 1, in other cases, the depth we're interested in. And the way we'll be measuring the circuit size is via the number of gates in the circuit. We're also going to be assuming that all of our circuits are layered circuits. That is, for each level of the circuit, either all the gates are ANDs or they're all ORs. The other complexity measure we'll be talking about is the bounded bottom fan-in constant depth alternating circuit size of a function f, denoted as AC0 sub D plus a half of f. The plus a half comes from the fact that while the circuit is still depth D plus 1, this bottom layer has a bounded fan-in, with the bound being logarithmic in the size of the circuit. So this bottom level here isn't exactly a full level of the circuit. It's restricted compared to the others, hence plus a half. In addition, we won't be talking about the search or the strict decision version of MCSP. So we'll be looking at this gap MCSP problem, which is this promise problem where the yes set consists of all truth tables of functions over n bits, where the AC0 depth D circuit size of f is at most S sub yes, and the no set is a set of all truth tables over n-bit functions, where the AC0 sub D size of f is strictly greater than S sub no. And you can think of this as being the approximate size version of MCSP, as we're trying to find the approximate size of the function f. That being said, let's move on to our actual results now, starting with the lifting theorems. So our lifting theorem is the following. Given some function f over n bits that has AC0 sub D plus a half complexity s, we're going to compose f with the parity function over roughly log s bits to construct f prime. The theorem we get is that for any such f and the f prime constructed from f, the AC0 sub D plus 1 half complexity of f prime is at most s to the power of 6 and at least root s over 3. That is, the higher depth complexity of f prime is within a small polynomial gap around the complexity of f in the lower depth model. So we're going to start off with C prime, which is a small depth d plus 1 plus a half circuit that computes f prime. What we're going to do is we're going to hit C prime with a blockwise random restriction rho. So a blockwise random restriction works by dividing the inputs of the function into blocks. So say we have some function over these bits here. We're going to divide this input into blocks of equal size. And then for each of these blocks, we're going to take one input in the block and leave it unset. And for every other input, we're going to map them uniformly to 0 or 1. So after applying this random restriction, what is the complexity of C prime going to be? What will it compute? Well, first off, we know that f prime is equal to f with a bunch of parity gates at its inputs. So, if we divide the inputs up into blocks based on which parity gate they feed into, then after applying a blockwise random restriction, the resulting function will just be f, with possibly some inputs negated. So what we want to know now is what happens to the depth of the circuit after we hit it with a random restriction, what happens to the size, what happens to the fan-in at the bottom. And this is where we use our new blockwise switching lemma. So our lemma says that for any KCNF phi restricted to some restriction sampled randomly from the set of all blockwise restrictions has no 2 to the t term t DNF with probability at most 8k over L to the power t. This should be compared to Husted's switching lemma, where using similar notation to what we have, his result would look more like 7k over L to the t. But that doesn't guarantee that one input in each block is left unset, which is vital for us. This is why we had to come up with the blockwise switching lemma. Using that then, what we're going to do is the following. We're going to take C prime, and we're going to look at all the CNFs at the bottom of it, and we're just going to assume that they're all CNFs at the bottom. By choosing T correctly, and by that I mean T is approximately log S, when we look at C prime restricted to rho, with non-zero probability, we can write each of these CNFs as a S term log S DNF. And once we have that, we haven't changed anything above this layer in C prime. So above those are still a bunch of disjunctions. So we can then merge these two layers to obtain a depth D circuit. And the size of this circuit is going to be S. Moreover, the fan-in of each of these bottom DNFs is also going to be log S. So we end up with C' restricted to rho for some blockwise restriction rho computes F. And moreover, that restricted circuit can be computed by a AC0 sub D plus a half size S circuit. Great. That gives us the F circuit we were looking for. For our other direction now, what we want to show is that a size S AC0 sub D plus a half circuit for F lets us construct a AC0 sub D plus 1 plus a half circuit for F prime with size at most S to the 6. So the first thought would be to just use the naive composition. That is, we just take the CNF or DNF for L bit parity and compose it with the existing circuit for F. Unfortunately, the resulting circuit is too large for the reduction we want to show later. So instead, what we do is what we call clever brute force. We're going to rewrite the parity over L bits as a composition of two separate parities, one over L1 bits and the other over L2 bits. This is similar to the standard way of constructing a depth 3 circuit for parity. You would split the parities into equal sized groups of bits and just compose the two. Here, however, we're going to choose L1 and L2 carefully to obtain the fan-in properties and the size properties we want from our circuit. So once we split the parity over L bits up like this, what we do is the following. We take the F circuit and we're going to look at these bottom CNFs or DNFs of the circuit, similar to before. And what we're going to do is we're going to take these L1 bit parities and merge them together with this circuit in a way that preserves the overall depth. So here we started with depth D. And here, in this resulting circuit, we also have depth D at some cost to the size. Then, once we have this, we're just going to compose it with the naive CNF or DNF for the parity of L2 bits. And that will give us a depth D plus 1 circuit. The fan-ins at the bottom will be restricted by L2, which we will choose so as to be at most 6 log S, the size bound we end up with at the end. And we compute F composed with the parity over L bits. So with this lifting theorem in hand, we can turn this into a reduction now. The first step of converting this lifting theorem into a reduction is going to be using a fan-in versus size trade-off to get a bounded bottom fan-in. What this means is we're going to increase the size of the circuit, but in doing so, we'll be able to bound the bottom fan-in overall. Then we're going to apply our lifting theorem, and then we'll just reduce back to unbounded bottom fan-in. From this, we get the following depth increasing reduction. For any d greater than or equal to 2, for any alpha less than delta in 0, 1, there are constants beta and gamma in a comparable range to alpha and delta, such that AC0 sub d plus 1 and gap MCSP, where the yes instances have circuit size at most 2 to the nth the alpha, and the no instances have circuit size at least 2 to the nth of the delta, is quasi-polytime reducible to AC0 sub d plus 2 gap MCSP, where the yes instances have circuit size at most 2 to the nth of the beta, and the no instances have circuit size at least 2 to the n to the gamma. In analyzing our reduction, we start off with this fan-in versus size trade-off. So here we start off with our depth d+1 circuit for F. And as a result of that trade-off, we can bound the fan-in by log S, but at some cost to the size. Next, we apply our lifting theorem, and we lift by composing with the parity function. So the circuit we get out of that has depth d+1 plus a half. These parity gates at the bottom aren't actually present in the circuit. We always use and or not. And their fan-in is bounded by L. So the overall circuit is of size at least 2 to the L. So the fan-in of these bottom gates is bounded by log the circuit size. Then to get back to unbounded fan-in circuits, we're going to compose with yet another parity, this time just over 2 bits. And we show in the paper that after this composition, you get a function which requires depth d+2 circuits of comparable size to your original function, but now the fan-in of the circuit can be unbounded. Finally, we're going to give barriers to obtaining better reductions for gap MCSP problems. So in Kabanets and Psi, they showed that nice reductions of NP to MCSP imply circuit lower bounds. And what they mean by nice is just that the length of the MCSP problems generated only depended on the length of the input instances. It didn't depend on the exact values of these instances. We show that nice in the same sense as Kabanets and Psi, and efficient reductions between the different depths of AC0 MCSP problems imply either breakthrough circuit lower bounds for AC0, or they lead to improved AC0 sub D MCSP algorithms. With that being said, we have the following open problems. The first open problem is the NP completeness of this average case AC0 sub 3 gap MCSP problem, whether it is complete or not. Another open problem is to try and tighten the gap in this lifting theorem. By tightening this gap, we obtain better results in the reduction. Finally, we would like to find evidence for or against AC0 sub D MCSP having improved exponential time algorithms, as this would rule out one of the arms in our win-win analysis before. Thank you for watching.